Welcome to this Houdini adventure. Today we want to take a look at an advanced Vellum setup that has multiple Vellum objects, including Vellum fluids, showing some great tricks to stay organized and controlling each Vellum object separately. In the end, you should be able to create a simulation like the one you see on screen. We won't recreate everything from scratch, but rather it's more like a scene overview to give you a general idea on how it worked. Before we jump into Houdini, I want to show you our asset library, where you can find all the assets used in this project. Each of those is a high quality scan with PBR, 8K textures and clean topology and organized UVs. Just visit the link below to get to our CG Trader or Gumroad page and see if there is something you can use for your own projects. In Houdini, we simulate every object with a low poly version and use it to transform the high poly mesh. So in order to follow along, you can also just create simple low poly meshes yourself and simulate with me. Inside Houdini, I first want to give you a quick overview of the project and the different steps we will tackle in this tutorial. In the object level, we have two setup containers, one containing our Vellum simulation and the other one a particle simulation that creates small droplets. Then we have a different render container in red that imports each anticipated asset from the simulation and creates materials. Also, we create a camera along a path with a look at null and a focus target, as well as some lights. At the end of the video, we will talk about why it is handy to have render container and how we can create such a camera, so stay tuned. Let's take a closer look at our Pancakes simulation container. We dive inside, and you can see this is where the Vellum simulation takes place. Here we import all of our models, place our Vellum constraints, simulate it, transform our high-res mesh onto our low-res simulation, and then do a little bit of cleanup and post-processing at the end. Let's take a closer look at one of those. For example, the pancake. With the file swap, we import our model, FBX. Since it's in centimeter, we convert the units to meter. We want to work in the real scale. And then we use a cleanup just to clean up and leave us with the attributes we actually need. In this case, just the UVs. In order to visualize the texture on the model, I use the UV quick shade just to get a preview. That also helps in the process. When you mess up your UVs, you will notice it when the texture is not working anymore. Which is also great to have is always a group with a name. So later on, if we want to split it after the simulation, we have all of our pancakes in one group. This is why I create a point group with the group name $OS and call the name the node pancake. Now we have a group called pancake for our pancake. Now I use the out high-res pancake. Now let's remesh it in order to get a low-res mesh. And this is the pancake we want to simulate. It's way faster and also Vellum handles it better since we have evenly spaced points. You can see on our high-res pancake, for example, we have more dense points on here, but less density on the points on the outside. And Vellum gives each point a mass, and this is why we have more mass here. So it's heavier in the middle and less heavy on the outside. And in order to avoid that, it's better to have a remeshed triangle mesh with even spaced points. So this is our out low-res pancake. One more thing that is important to mention here is that the low-res pancake at least represents the volume and shape of the high-res pancake. So when you have a very low-res mesh and it doesn't fit here, you might have some clipping later on when you simulate different objects together. Just keep that in mind. Now we copy those pancakes onto our points. Those points will determine the initial states and also set initial attributes we will need later on for Vellum constraints and also for post-processing. So let's go one by one for each node. I will just deactivate all of them, and the first node is the line. So here we can set the origin, also the direction and length. The length of 0.2 will be 20 centimeter, and we can set how many points we have in that line. And you can already see that we have quite a lot of control on the initial position and how many pancakes we want to have. Then we want to point jitter a little bit and then set a p-scale attribute. The p-scale attribute will be set with an attribute adjust float. It will give you a lot of handy operations to set your attribute. You will also have one available for integer and vector. And in here, I want to use the setInitial operation with the random pattern type. You can also use a noise, for example, and then a min-max value between 1 and 1.1. This point, we can also open our geometry spreadsheet and see here the p-scale attribute from 1 to 1.1 on our pancake. Since it's a keyword, the copy node will automatically know that it shall adjust our pancakes. Now I create an attribute wrangle to store the p-scale in another attribute. I do that because Vellum usually when simulating overrides the p-scale attribute and I want to keep it for later on. So I use the r_p-scale to store the p-scale information, and once Vellum overrides it, I still have access to that information after the simulation. So I know, oh yeah, this pancake was, for example, 1.1 p-scale in size. Now I want to set the set pieces attribute. You can see that it also does nothing to our pancakes, but it just initializes an attribute. The p-scale will be the point number. So for each of those points on the curve, they have a point number, you can see on the very left. And now it also has a piece attribute. For example, the first one has 0. And now all the points later on, when we copy our pancake on here, will have the piece attribute 0. The second will have the piece attribute 1. And then later I can, even after simulating, say which pancake will be which piece in order to separate them. Now let's set an orient attribute, which will flip 50% of our pancakes and also rotate or orient them randomly -5 degrees to 5 degrees in X, Y, and Z. So to do so, we need 4 quaternions. First one to flip our pancake, the second, third, and fourth to rotate them in Y, X, and Z. We create them, for example, the rot Y. It's just a random ptnum, so a random value from 0 to 1, fitted to -180 to +180. And this is the axis, the y-axis, and we want to rotate them -180 to 180. For the x and z, we just want to give them -5 to 5. For example, let's say we give them -1 to 1. You can see it will not be that strong. So we create those quaternions, and then we have our orient quaternion made of our normal and our up vector. And to have them affect this orient quaternion, we can simply multiply it. So you can use the q multiply, set our orient attribute, so vector 4, with our rot y and rot x and rot z. And then we use an if statement. So if the random number ptnum plus seed is smaller than 0.5, so 50% of our points, it will also multiply the orient with the flip quaternion. So you can see with the seed value, I can now say how many are flipped. The orient attribute and especially quaternions can be quite frustrating and difficult to understand. I can recommend you the Tokuru website. There's a whole section about the orient attribute and how to manipulate it with the different functions Houdini and Vex offer you. I will drop you the link in the descriptions. Maybe check it out. I also always come back here to look up certain things. So now what I want to do is I want to set a density attribute based on the layer. You can see now that on the very bottom the density is high, and on the very top the density is very low. I need this density attribute for our Vellum constraints later on, because I want to make this pancake quite heavy, but it will be even lighter when we go up here, because Vellum has a little bit of difficulty when we have the same weight on the very top. It will just squash everything. So in order to do so, we have our ptnum, and the ptnum is fitted. so for the PT num is 0 to 5, and we fit it from 0 to the amount of points we have. This is just an integer channel, and we linked our line points here. And I want to fit it to 0 to 1. And now I remap the whole thing. So now you can see here, if you watch those values and I adjust the remap, I can quickly remap on how much weight every pancake has. The last thing I did here is just to set an initial velocity, also with the attribute adjust vector node. So when we copy those 2 points, you can see that each of our pancake receive those initial attributes. Now I created a group, called it pancake sticky. So I saw that when our ingredients fall on top of the pancake, a lot of them just fall down, but I want them to stick a little bit to the top surface. And in order to do so, later in Vellum I will show you how to do it. We need this group. Okay, so now we set the constraints. It is basically Softbody. Vellum configures strut Softbody. This will give you 2 nodes, the Vellum cloth, which is a constraint from point to point. So the connected points next to it. You can also say the neighbors, it will connect to them. They also have different attributes like stretch and bend stiffness. And also we have struts. To maintain the volume, we have primitives going from the top to the bottom. So to prevent volume loss and just make it a soft body. So on here, all I did is playing around with the stretch stiffness and also the stretch and bend stiffness on the vellum cloth, as well as the damping ratio. So damping reduces jittering and also a little bit of bounciness. So when I did it without the damping, it was quite bouncy, and now it was just I didn't know these values beforehand. I just created them while making trial and error, just simulate it again. They always depend on how many substeps your Vellum Solver has, also on the mass of your object, and also of how many points your object has. So there's really no guideline to that, but maybe just try it out, test each value separately, and then simulate it. So I created output nulls, one for the geo, one for the cons, and here I have an object merge. Usually, if you have multiple objects, you can just use the merge node and merge the geos together and also the constraints together. I find it a bit more organized if we just use an object merge, and you can have multiple inputs in here. So the cool thing is that you can now deactivate inputs, and you can see that we now have only our pancake. Maybe let me quickly disable the fluid inside of here. We will get back to that later. And now we can go to our Vellum Solver, which is has the geo, the constraints, and also the collider. The collider is right here. It's just a plate, the cloth, and then the ground. And on the Vellum Solver, I use the timescale from 0.5 and substeps 8. And let's start simulating. And you can see that it's quite fast. And as I said, all the values already, it has the simulation result I liked. And the cool thing is with the object merge is that you can quickly activate and deactivate different Vellum objects, and then simulate each separately to find out how they behave. And if you want to change the behavior or the stiffness a bit, you can always isolate them that way. So let's turn those back on again and have another look at another example here. For example, the blueberries. We import the blueberry, we convert it to meters, and now we match size so they are on the origin, clean it up. And for the blueberries we have variants. So we have 4 different blueberries. With the blast node I separated each of those, used the UV quick shade to set the texture, added a variant attribute. So it's just an integer point attribute called variant, and this is the variant 0, this is the variant value 1, variant value 2, and variant value 3. Merge those together, created a group like we did before. This is our high-res blueberries. Now we remesh each of those, use the connectivity to set another variant attribute. And now if we copy to points, the initial points here is just a grid and a scatter points onto it. Then we have our point jitter, p-scale, or orient. In this case, we just have an attribute randomize with the orient value randomized, and then we have the velocity. And now we set an integer attribute called variant in here, which equals the variant we have on our blueberries. So that way, our copy to points node already has this piece attribute variant. We just need to check it. And now you can see that we scatter the variants, different variants per point onto here. So one more time, the points have variant values from 1 to 4. Each is there to copy a different variant of our blueberries onto the points. And the copy to point now handles that for us. Same with the initial state. They copy it to the position of our points. If we change the scatter, we have more or less. If we change the p-scale, we have smaller or bigger ones. You can see that it's quite handy and very controllable. Same thing here. These are soft bodies, so we use the vellum cloth and also the struts constraints, set everything up, and this is our out geo and out constraints for the blueberry. We also merge those in here. So I did that with the bananas, it's the same, and also with the raspberries. Well, you can see always it's color coded. The blue ones are the geos, the yellow ones are the constraints, and the red one is the collider. We can take a quick look at the collider. It's just the plate and the cloth. Those now go all into the Vellum Solver, and maybe I can quickly show you the cached simulation. They work nicely together. One thing to keep in mind is that the ingredients falling onto the pancake need to have a different mass, so lower density than the pancakes. Otherwise they are very heavy, and you kind of have to figure out that the proportions are right. So on the vellum cloth, we just saw that we have very low density for the blueberries here. Otherwise the blueberries will fall onto the pancake and squash it. And then it's way too heavy. So you need to figure out, first of all, a good mass for your pancakes, and then everything that's falling on top and maybe also interact with each other, you kind of have to set in relation to each other when it comes to the mass. Before we start simulating, I have an intersection analyze here. This will analyze if there are any intersections, because Vellum does not like that for your Vellum geometry. Always check that there are no intersecting geometry. If you go now middle mouse, press on here, you can see 0 points. That means I couldn't find any intersections. That's just to double check. Now let's talk about the fluid first. Okay, we have the syrup fluid here. And for those, I just set up 2 spirals. You have this lap spiral SOP, which is quite great. You can set up multiple helixes and then use the height and the loop and the radius for that. And it's very adjustable. And these are basically the path for my emitters to run. So I transformed it, push it up, pushed one primitive up a little bit more. So to create the spiral, and now for each of those primitives, I want to create a point running over that primitive from 0 to 1. For that, I go into a for each primitive loop, and in here we have an attribute wrangle. Maybe let me visualize the point a bit bigger. So you can see now that this point is running along my curve. Maybe let's template the curve, and I can animate it from 1 to 0. So in order to do that, for each primitive, we want to create a position vector, and the position vector is created via the primuv function. The primuv function requires first the first input, then we want to have the position from our primitive 0. Up here, you can see that we have 1, 0, 0. This is one primitive in here. Here, now it wants a u value, So the curve is always one view value, one dimensional, just going from 0, 0 to 1 on the top. And this gives us the position on that specific u value. So u value of 1 gives us this position in space on top. If we have 0.5, this is the position it will give us. Then I remove that primitive and added a point on that position vector we asked for here on that primitive. And that's the way I can then animate the u value and get 2 points along the curve. I also added a mountain node, so they just get a little bit of wiggling to make it more organic. And I also want to create a trail swap to compute the velocity. That's quite important for our points to later behave correctly. So if we visualize the velocity, when we have the emitter and we move it around, you want that movement, the velocity from the movement, also added to your simulation. If we now copy those 2 points, and these are just a sphere, you can see that the sphere gets the velocity. Okay, now instead of a Vellum constrain, we create a Vellum configure grain. And this node is there to not only create grain, but also fluid. We can create points from volume. We can also create a points from volume node and then deactivate it and do that manually, but I just like to create points from volume with this particle size, pack density, and just played around with those values here. Especially for thicker fluid, viscosity is quite important. The density, of course, how much is weight. I had some trial and errors where it was way too heavy and then squash all the blueberries. And I like that you can now with the Vellum setup have a lot of interactions between all of those different kind of materials, but then just keep in mind that the density is set properly to make it behave right. Then also a little bit of surface tension. This is also just coming from trial and error. I want to create a group, and then I have also the out geometry as well as the out constraints. Okay, those particle points are not just being put in here into our object merge. We want those be emitted on each substep or each frame, depending on what you need. And to do that, we dive inside the Vellum solver, and you can see here is a output null source already set for us. And then you create a Vellum source object, and now you can set a sub path, target path, and constraint path to our scirip geo and con, and say emission type on each substep with a particle density of 2. That's also something I played around with just to get a good feeling for how it is flowing. And we want it to emit until frame 75. So with that setup, now those particles are emitted on each substep, and we have 8 substeps. So okay, so now let's turn them back on again. And one more thing about art directing it. So as I mentioned, all the blueberries were falling down the pancakes, but I want them to stick onto the pancakes. So what I did here is you can, if you set constraints on your geometry right here, they are set initially. So on the first frame, they're being set, and it knows those constraints are there. They will not change over time. If you go onto the Vellum solver and you create a Vellum constraint in here, you can create constraints on each frame. Then it will check each frame if it can create constraints here, and those are more interactively. So what I did here is I took the blueberry group and I created a glue constraint onto the pancake sticky group, the group we created on the top pancake, and I searched on the max distance, and if it finds points in here, it will create constraints. They will also have a detach object chance and also a breaking threshold, but I don't want them to really stick on it, but kind of just hold onto it as long as they can, and that really helped to make them fall onto the pancake in the end. Okay, so let's have a look at the end frame. I cached everything until we are at frame 100. And one thing for the file cache, I created the file cache with the $FF sign because I wanted to also cache substeps. So we have 400 files in here, 100 frames, each frame containing 4 substeps. Just so I have a little bit more information about the movement, and later for retiming and having slow motion, that's quite important to have all those position data for the in-between, since when you have it falling in real time, it's actually quite fast, and it will strangely interpolate the positions if you don't have enough data. Okay, so now let's go in. We still have our low poly geometry in here. We created those groups for each of our Vellum objects, and I created a little subnet to take the high-res pancakes and replace them with the low-res pancakes. So on here I added my group. It's called pancake, and what it does, it takes the low-res animation, the whole animation, it blasts everything but the promoted pancake group, so now we only have our pancakes. We freeze it on the first frame, extract the centroid points with all the attributes and all the groups, and we run over the pieces attribute, which is quite important. We still have the pieces we created earlier. I want to reset my p-scale with my stored p-scale. You might remember the p-scale here, on here. By the way, if we extract the centroid with all the points, we get a lot of attributes. But we also get all the orient attribute, for example, we created, and the p-scale we created. The p-scale is here quite small, but we stored the p-scale in this r_p-scale to reset it. This is what we do here. And now we can copy our high-res pancakes onto those points. And as you can see, the low-res pancakes on the first frame, and now the high-res pancakes are the same, on the same position. This is great to use it for a point deform. We want to deform our high-res pancakes with the lattice, rest point lattice is our freeze frame, and the animation is our deform points lattice. And now you can see our high-res pancakes are being deformed by our low-res pancakes. And we do that for each of our Vellum objects. For example, for the blueberries, just keep in mind that you also have to turn on variance here, since we have our variance, and it works the same. Okay, so now let's go into post-processing. We object merge all of those geos from here again to our Vellum. We split it. We only have our ingredients now on the one side, and we have our high-res ingredients on the one side, and now we have our liquid on the other side. I want to retime everything, and in order to do so, I want to separate my liquid first. Otherwise, it might mess up your retiming. Since we have a steady point count here, but a not consistent point count here because we are emitting particles. So the retime node is quite easy. We just don't want to use the velocity when interpolating the position, and we want to scale the velocities. Also, we just need to run over the position attribute. Each attribute will stay the same. Since we scale our velocities here, we don't have to retime it. We take for the retime of 4 substeps. Okay, so the other retime node is basically just a reference from that other retime node. So if you create right-click, actions, and then create reference copy, it will copy that node and just link all the parameters to the other one, since we want to retime it exactly the same. Then I linked the by frame method frame to our output null outside here. On here I created a float value. Now I can kind of control the whole retiming from outside. I don't have to dive into any setup. For our fluid simulation, we use the VDB from Particles to create a VDB, and then use some VDB operations to get rid of those small droplets and also smooth the mesh. We convert it to polygons, take a color, and then we have to transfer the velocity from our points. Since we lost the velocity in the meshing process, we transfer it back to our liquid, and then we reassign the group, and we merged everything together. and that's our out post process for the Vellum sim. So inside the droplets, we object merge all of our ingredients as well as the pancakes in here, but not the retimed version, before the retime. We want to do everything we simulate before retiming it and then retime everything together. We just used a popnet to create particles, and we used the pop source scatter onto surface. We want to just simulate particles until we are at frame 24, set the birth rate, how many particles we want to have, also a life and an age. We also create a drag and a pop speed, just play around with that, and of course use our ingredients as colliders. We clean everything up since those particles also come with a lot of attributes. We just want to stick with those we need. And now we cached everything, and you can see that we just have those droplets falling with the ingredients and interacting with them. Okay, so now we set a p-scale, and we set it by the ID. Since we have a changing point number, we want to set it via ID. Add a little bit of p-scale, set it the p-scale, multiplied it with age, divided by the life. So when they are born, they are at 0, they get scaled up, and then when they die, they dive back again. So we don't have any popping particles in here. We use the retime, again, just with the, our retime frame from outside connected to it. And then, we created this attribute adjust flow, just it multiplies the value just to test how big they have to be. And now those droplets get a water material later on. So we take all of our simulations and create those render containers. For example, we have the pancake. For that, we just take an object merge, and from our out post process, we can object merge a group. And since we set our groups, we can simply go to pancake, import the pancake group, and now only the pancakes are inside of here. We also use a clean node just to get rid of everything but the things we need. On the pancake geometry, we now set the material, and we do that with everything else. So we have all the render container for a simulation. So it's very easy to quickly turn everything off, just have the pancake and then make some look dev, for example. Maybe we can quickly do that. We can just go to camera 1, and now you can see we only see our pancakes. Now we can also isolate the banana, which is quite good. So we can quickly go over each asset, make some look dev, and then use the display flag to turn everything back on again. So that's very handy to make some quick look dev. Here we have some set dressing. These are just assets from our library imported to make it look a bit more appealing. So for those, maybe let me turn off the background so we can see it a bit better. I also created a camera. In order to make it faster, I just want to quickly hide the simulation. Maybe just take the plate and split the views. So 2 views, and on top we can see our camera. What we did here is we created a camera and also a camera path. So you can see that this is also a spiral, and we want to have our camera go along our path. The way to do that is on the camera, on the transform, you can here set enable constraints and create a constraint network. If you dive inside, you can see that we now have our camera and a constraint path node, and we can here point to a path we want to set our camera to, and then we have the position to animate it. This parameter I just promoted, and I created a parameter on the camera to quickly do it here. For the look at, this is just a null, and also under the constraints we can set a look at node, and we can bring in a constraint object which is points to our null. And now wherever I move the null object, I'll quickly show you, call it look at. You can see that the camera is looking at that null. Put that in the middle of our plate, a little bit up, and also can animate that. For the focus, so the depth of field, we need a focus distance. The camera, I'm using Redshift for rendering, and I enable depth of field, and I disable use Houdini camera focus and just set the focus distance in here with an expression. So the expression is v length and then vt origin. And now we set it to our focus target. And this calculates the length, the vector from our camera position to our position of this focus target, and set that value in that focus distance. So now we know where our focus actually is in space. So after turning everything on again, quickly created a few lights, which is just having an ambient light, which is a dome light, also a top light from above, especially for the round objects and the liquid. It's always nice to have a top light. We create a few background lights just to make the background brighter. Those don't affect our pancakes. And I want to have a key light, and you can see that I have a null object linked to it, and I animated it, so it's rotating around with the camera a bit. That's about everything I wanted to share with you guys. I hope you liked it. If you have any feedback for me, please write it into the comments, and see you next time.